network layer. So we are moving one layer down. We finished TCP, and the one layer down is what? What protocol is there? IP. Right. So this whole chapter is about IP. I mean, not just IP, but there are other protocols that run at that layer. So we talk about network layer basics, and then we talk about IP version 4, ICMP, DSCP, NAT again. Actually, we have done enough NAT, so we don't need to do too much. But we do NAT, and then we go to IPv6. Then we also talk about routing. Now, believe it or not, IP doesn't do routing itself. IP is not a protocol for routing. For that, we have some other protocols. They are called RIP, OSPF, and BGP. And they are in two categories, link state and distance vectors. We talk about those categories and then those protocols. All right. So there are lots of protocols to talk about in this layer. But before we go to those protocols, we just want to cover some basics of this layer, and that includes how the forwarding and routing is done, how it is done in other networks, ATM networks, how the classes of service are done in other networks, and what are the components in the router and how the packets are queued and so on and so forth. Now this is nothing to do with IP as such, but this is general thing applies to most protocols, and in some places IP has made a choice which is different from other protocols, so we talk about that. So we gave you a list before, but interestingly enough, not the protocol that I gave you the list, they run in the layer 3. In the layer 3, only two protocols run, IPv4 and IPv6. So these protocols, DHCP, RIP, OSPF, BGP, they really run on the top of TCP. All right? And so technically, you could call them application layer protocol, but they're not really applications because you never see them. You never see DSCP yourself. I mean, you actually see, because you cannot run Microsoft Windows without knowing your DSCP server and things like that. But RIP, OSPF, and BGP you don't see because the routers use them, and they are kind of used for networking to help send the packets around. So we'll talk about them as well. And ICMP is another protocol which actually runs on the top of IP. It doesn't use TCP. It runs on the top of IP. That we will talk about in this set. Okay. So IPv4 and v6 are called forwarding protocols, not routing protocols. So there is a difference between forwarding and routing. And the difference is, forwarding means you look up a table and you find out where the packet has to be sent. Any clerk can do that. Routing means to prepare that table. That means you have to know who is connected to what, complete network map, and then figure out that to go from A to B, you should go by that door. Or to go to A to C, you should go through that door. So that table preparation is called routing. And so IP doesn't do that. IP doesn't prepare the table. IP simply uses the table. And therefore it is a forwarding protocol, and the protocol that prepare the table are called routing protocols, and they are this: RIP, OSPF, and BGP. They prepare the table. Yeah.
Where's that table stored?
So table is stored in your basically router. So when a packet comes in, the router looks into the table, and I will talk about that in a minute, actually more detail. This whole lecture is about that anyway. So first thing you have to understand is the difference between routing and forwarding. Right? Routing is preparing the table, and forwarding is using the table. Yeah.
So if there's a router that has no static table where all their routing?
Yeah, so they may not. So for example, yeah, good question. Yeah, so I mean, that's a good question, whether it does do routing or not. But there were routers in the beginning of time when there were no protocols like this, and the tables were made manually. So somebody sat down and wrote the tables and put it into the router. And so they were routers at that time. I mean, today we won't have such a thing because the world is too dynamic.
Yeah, like in small networks.
In small networks, you could do static routing.
So is that considered routing?
Yeah, that's routing. Basically, preparing the table is routing, whether it is manual or automatic, doesn't matter. And in the phone network, actually, it was manual for a long time, even after IP had automated it. Okay, but now everywhere it is automated. So that is one thing, forwarding and routing. And then there is a control and management. So management has to do with, actually these are more of a control protocol, and management is not in this list. But since I use the word control and management, let me explain what is control and what is management. So suppose you work for a company, there are 100 people and there is a manager. Suppose manager is sick for one day. Does the company stop? No, company continues. So the managers are people who are really totally optional. They're not required. They are really not required. The reason they are there, if out of the 100 people, one person doesn't do the job, then the manager is watching everybody. Right? If somebody gets sick or somebody is not performing the job, so management is there to look after, to detect the faults. Right? But if there is no fault, the managers are sitting there doing nothing. If everybody is good, if you just hire the 10 best people from WashU, then you can be a manager and sleep in your home. Right? Because they will all do their work. So the managers are management part of any computer systems or network is that part which is basically mostly related to making sure that the system is operating fault-free. And it is totally optional because if there is no fault, if the system is very reliable, you don't need the management part. Control. So there are two parts left, data and control. Data is the part which is sent by the user. So you want to send a message, that is data. Control is the part that is added by the network itself. Control is something that you didn't produce, but it is required to send the message. This is the required part. So if I don't put a header, the packet will not go anywhere. Right? That is control. And control can be either in the type of header or it could be additional packets. So routing packets. So RIP and BGP, they exchange lots of packets to figure out what the right path is, who is connected to whom. Those are all control packets. Because those packets were not produced by the user. They were produced by the system to serve the user. Yeah.
So there are management packets also, or just control packets?
Yes, so there are management packets also. So for example, and this is not on this list, so that's why this will come in chapter 7 or 8 someplace when we talk about management. Network management, using network management, a router could, network manager could send a message to all the routers saying that please tell me how many packets have you forwarded, how many packets were in error, how many packets were dropped. Those requests and responses are management packets. Right? They are not in this one. So in this chapter we have data, control, only two. All right? So IP mostly handles with that data part, but the control part is handled by this ICMP. ICMP is IP Control Management Protocol, Control and Management Protocol, it's called, okay? And this is all control. The routing protocols are all control protocols because they are really, the users don't see them. Users don't produce them. Users just, they are done by the system to make sure that the user's job is done. So I want to double check. Everybody understands the difference between data, control, and management. Yeah.
Routing protocols are all control protocols?
Yeah.
Okay. Could you explain why?
Because they don't contain anything that the user sent. If you get an OSPF message, it has nothing that the user sent. It simply says, that A is connected to B with a link of speed X.
What's a control protocol which is not a routing protocol?
What is a control protocol which is not a routing protocol? ICMP. And by the way, this data control and management applies to every layer. At the transport layer also we have data control and management. At the application layer also we have data control and management. At the second layer that we will come to later as data control and management. So for example, when you do HTTP, there is data control and management. Why? Because data is what the user sent, control is what is added by the system, all the headers, right? And the management is something that you don't see, but somebody could be monitoring as to how many requests they are sent today, how many users came in, how many distinct users came in, how many distinct IP came in, all that is management.
So I feel like management is like an application.
Management is also runs at that layer, application layer. It's not on this list, but yeah, SNMP is the name of the protocol.
So management protocol is application level.
They run at application level, yeah. So anyway, again, let me say, any bit on the network could be classified as a data bit, control bit, or a management bit. Because that bit was sent by the user or generated by the system for operation or for management. And the difference between control and management is very fine. I have not seen it written in any books like that. I don't think even this book talks about that clearly. So I just want to make sure that you understand that difference clearly. Data, control, and management. Management is the optional part, which is something required if something fails. If nothing fails, you don't need the managers. They are called overhead.
How about like SSH?
Eh?
SSH, is that
SSH. Now I will come to SSH later on, but let me just say SSH is an application.
So is that, no, but that ICMP is also,
Huh?
or not ICMP is also application.
No, ICMP is not an application. I will tell you what ICMP is. You don't know ICMP. I don't know whether you have used ICMP. So anyway, is the difference between data control and management clear? Everybody clear? Okay. All right. So now we go into forwarding and routing. Forwarding is basically done by looking at the address prefix. So if the prefix of the address, so we look at the packet address is generally 32-bit long, and there is a table. In that table we don't have 32-bit quantities. What we have is a prefix, so some part of the address. So the prefixes are written like this: 126.23.45.67/32. That means the first 32-bit of this thing, which means all 32 bits of this thing. Or you could write down as 128.272.15/24, that the first 24 bits are like this. Or 128.272/16, that the first 16 bits are like that. And doesn't have to be 8, 24, 16, it could be here 18. First 18 bits are like that, or it could be 14, first 14 bits. So you just take the first 14 bit of this, and that is the prefix. All right. So prefixes are written by the number followed by slash followed by the length. Okay. And so the table will say if the prefix is this, then the next router is that, and the interface is this. So let's see. We are talking about next router being this. So we are here. We are here, and if we find that some packet has the address matches this one, then we have to send it to this router on interface 1. So interface is 1 and 2. There are two interfaces.
Can you send it to different routers from the same interface?
Yeah. You can send it to different routers from the same interface, because there is a connection like this Ethernet connection, and there could be many computers connected here, many routers connected here, and you could have only one interface on which you could send to many routers.
How does the server that accepts those
No, except the people who have that address, they will pick it up, others will just ignore it. So basically that is, when we go to Ethernet, then we'll talk about that, how Ethernet works. But for now, let's just assume that everything is point to point. So on every link there is only one thing. Okay? So a packet comes in, we look into this table, and this table says that the first 32-bit match here, then the next router is this, and the interface is 1. If the address matches this, then the first router is that, and the interface is 2. If the first address is this, if the address is this, then that. Now it is quite possible that the address matches many entries in this thing. Okay, for example, if you had the address 128.272.15, it will match this entry as well as that entry. Right? So we use the longest prefix match. So we don't use this entry. Which entry we will use? The one that has the longest match. So we start from the top, which has the longest entry, and as we find the match, that's done. Right? Because we start with the longest one, and then if we match, that's be done. That way we don't match again with the shorter ones. So forwarding is done from input link to output link via address prefix lookup. The routing is making this table, and then we do the longest prefix match. So there are 3 concepts on this slide. What is forwarding? What is routing? What is longest prefix match? Okay? Clear what is longest prefix match? Now, from now on, in these slides, I have put at the bottom something that you can do on your own. And the reason is that some people wanted to know, students wanted to know as to what part of the book we should be reading or what should be doing. So it's not just the homework. So this is optional. So if you go to the book and there are review questions, so there is a review question R3, right? You should be able to do that after this slide or after reading that part of the book, right? If you're not able to do it, you can ask here in the class as to what does it mean. Okay, so this is not a homework. You don't have to submit it here. Just do it on your own. That way you will be a little bit ahead of the class, and then when the exam time comes, you will do better. So that is optional homework is the definition of that, okay? All right. So if you are in Windows, you can just go to a DOS box and say route print. And if you are on Mac, I'm sure there is a similar command that is called netstat -m. And this is what will print. Okay? It will say interface. These are all the interfaces that your computer has. Then it says if this is the destination, this is the net mask, then you go to this gateway with this interface with this metric. Alright, so that prefix is specified not by putting a slash, prefix is specified by putting a mask. So this is saying that we match the first 8 bits. 255 means first 8 bit, match the first 8 bit with this. 255.255 means match the first, how many bits? 16 bits. Because what we do is we take the address and AND it with the mask. When you AND it, everything that is 0 is cleared out, and only first 16 bits are left. Right? Our first 8 bits are left, our first 24 bits are left, our first X bits are left. It doesn't have to be 824, it could be any number. No, so on the IP address you end the net mask and then you compare with the prefix. Right? If it matches, then you are done. If it matches, then you look at the gateway. This is the address of the destination where you want to send the packet to. This is the next hop. And this is your interface. Okay? Your interface means you have, in this example, you have two interfaces. One has the address 106, one has the address 108.
Didn't you say that it should be sorted by like the netmask?
So this is in some sense sorted, except for this last in the middle here.
The last.
Yeah, this is 32-bit. Yeah, so this is not sorted, but basically, so somehow they will have to find out the longest prefix match in this case. This is not sorted by that method. But so then this is the, so this could be wired interface, this could be wireless interface. Right? I'm coming to you. So then it will decide that if you get a packet, then you should go to wired or wireless. However, when you go there, if there are two matches, suppose they both have the same length, then you go to the metric and you select the lowest metric first. So higher means bad. So if the metric is 10, that is better than metric 20.
So it goes over them, and then it chooses first by the length, and then by the metric.
Metric, yeah. So generally, if you have both wired and the wireless at the same time, which one you should go first?
Wired.
Wired will have the metric 1 and the wireless will have metric 10.
How about if both of them have the same metric? Or is that
Yeah, then basically it is just random. Yeah, it's shown in this diagram. Yeah.
What's the difference between an ASCII of 255.0.0.0 and like 240.0.0.0?
Okay. 240, you have to expand that. This 255 is 8 bits, 8 ones. 240 is some less number of ones. Maybe it is 6 ones. Or 3 ones. I don't know how many. You have to just expand it. So that is not complete multiple of 8. See, this 255 is all 8 ones.
240 is
4 ones. Okay, so 240 is 4 ones. All right, everybody understands the net mask. Everybody understands this prefix and then the gateway. There are two gateways here, 192.168.0.1 and 192.168. So actually this is not a gateway, this is my own address in some sense. And then this is my own address. And these are the metrics. Now, and so the default gateway is 192.168.0.1. Okay? And 127.0.1, 127.0.0.1, that is a universal notation that whenever you have this address, that means you, yourself. All right? And whenever something begins with 224, that means a multicast. So that's not a one computer, that could be a group of computers.
netmask 0, 0, 0, 0. That means.
What is the first one?
Yeah.
Yeah, see now look at this. Any address will match this. So what you do, you get any address, you end it with 0, 0, 0, 0. What is the result? All zeros. Then you match it with this one, it will match.
So it will match everything. Right?
Everything will match this. So if it doesn't match anything else, then you will match this and you get out there.
So
This is the catch-all.
you have two of those.
That's the catch-all, right? Yeah. Oh, sorry, there was a question in the back. I said I will ask that. Can you ask the question again, please?
I have the same question. What is the unit of asking?
So you already asked? Okay, so go ahead, your question.
So if everything is 0, what do you match it to?
Everything is 0, then you match it to this line here.
I'm just saying. My question is, why is it first?
No, okay, whatever it is writing is not the way it is used inside the computer. It might be written in some order that I don't know.
So the computer is
Yeah, so basically the whole game here is to find the longest prefix match. So whichever gives you the longest length of the number of bits match, that is what the line will be used. What is mask ended with? So you take a packet you want to send, you take the destination address on that packet and you end it with the net mask and compare it with the first column. If the match, and that is the longest match, then you go to the gateway and the interface and the metric. Yeah.
Just want to repeat that. You take the net home destination and net mask, you end them.
Destination and the net mask, you end them, yeah.
And then if it matches something on the destination,
And then you match with this field, this column.
then you send it.
And then you find the longest prefix match. Right? It might match many, many entries here. So whichever is the longest prefix match,
You send it through that interface.
you send it through this interface to this gateway by this using this metric.
So gateway is the destination.
Yeah. Gateway is actually, if you want to be really correct, gateway is the next hop. Because destination might be over there in Germany, right? But next hop is the gateway. All right. So this you should be able to do on your computer, right? Now, not only should you be able to do this, you should be able to modify this table to your requirement. So that is your homework 4A. How to play with this table. All right, and this is what you will do first. You use the command route help to learn this message, this thing. This is not part of this course, by the way. I'm just giving you this extra because we told you this is not about Windows, this is not about Macs, this is about IP protocol, things like that, right? Everyone has a different implementation. Windows implemented using route help, Mac implemented using man route. So you learn it and then you ping to Google, that will give you the address of Google, and then you connect it via wired to internet, and that wireless link is also available. So you have to have two links to do this experiment. I think everybody has that, right? Everybody has a wireless and wired link. If you don't have wired link at home, you can do wired link in some lab here, student lab. So you need wired link and wireless link. So disable the wireless first. You have only one interface. Run ipconfig. Now what is ipconfig? ipconfig is the Windows command which tells you the address of your own. In Mac it is called ifconfig. To find your available links, print the route table, trace route to google.com using traceRT. So traceRT is the third command that you will have to run to find out how you can go to Google. So it will show you that you're going to Google. Obviously everything, since you have only one interface, where are the things going to go through? That interface, right? And you will see that in traceRT. Now enable wireless. So now you have two links. Run ipconfig to see that you have two addresses. Print the route table. Now the route table will be twice as big, right? Modify the routing table so that the preferred path for google.com is via wireless. Now nothing will go through wireless, by the way, because if you have wired and wireless, wireless is slower. Mac and Windows, they all know it, so they will send everything through wired interface. However, you want something to go through the wireless because you got two links, so why not use it? How can you use it? You modify the print table, you modify the metric command or something so that that becomes cheaper. Right? Cheaper means better. So modify the routing table so that the preferred path for that address, just one address, is via wireless interface. Now print the new routing table, trace route to Google and verify that it is using the wireless interface. Note the command you used to modify the routing table and submit, one line only. So you're going to do all this. I don't want to see all of this. All right? I need to see one line, and that is the key line. How did you modify the table? Yeah.
So do you want us to print the routing table or is it?
No, just print it for your own sake so that you understand what's going on.
So you just want the commands?
Yeah, print means you will see on this. See, the thing is when you say route print, it doesn't print on a printer, it shows you on the screen.
Okay.
It shows you on the screen. So you will see on the screen and you figure it out, you will get something like this and you see what is there, unlink is there and what unlink means, figure this out, right? And once you have done the modification, that is the key. Once you've done the modification, just print that out, and if you got that far and you wrote the right command, we are happy. All right? So it says here, your command should be modify. That table is the only one we need. One line only we need for this submission. All right? And second thing it says is, you have to modify the routing table that only one address goes to that one. Everything else will go to the wired interface anyway. Yeah.
How do we find out what the command is?
Okay, the command is route help. It's trivial. It's trivial. But having said that it's trivial, you should really experiment with many different things and see what the effect is. And I have done that. And as a result, I have many things that I can do on my computer, on my home, that many people cannot do. So for example, I have two DSLs, actually two DSLs I used to have, now I don't have it, but I have two DSL and I could say, well, this traffic should go through this and that traffic should go through that DSL. So you could divide your traffic according to the computers, according to the destination, according to anything you want. There are many computers in the home and I don't want to occupy one DSL, I want to keep one for something important, one for something which is useless. So you can do all that. So you have two interfaces, right? Right now you have no control over those interfaces, but after this command, you will know exactly what is happening with wireless when you are doing wired and what is happening with wired when you want to do wireless. Right? You can use both of them at the same time. All right? Okay. So that is so much about forwarding, and now we go to the buffering. And so when you are sending the packets are on the wire. So these are the bits, are the packets going to the destination, and suddenly when the packet is reached, the ACK comes back. So how many packets should you have outstanding? If you don't consider the destination, assume that the destination has infinite buffering. Destination has infinite buffering, then you should have so many packets so that the whole line is busy, because if you have less, then basically you are wasting that much time. Right? So the ideal buffering is equal to the round trip time, which means the whole line is busy, both sides, times the transmission rate. So if you have 1 megabit, you find out how much is the round trip time and multiply by 1 megabit. That many bits should be the window set, flow control window set. Because if you set anything less, you are not using the network fully. And therefore you should have that many buffers at the destination. However, not every flow should have that much window, or that much buffering, right? Because there are many people sharing that line. So it turns out the sharing is by square root. So if suppose 9 people are sharing, then each of them should have 1/3 buffer of this size. So some time ago, like 20-30 years ago, before my time, somebody did an experiment and said that the buffering is proportional to the square root of people sharing. So this is a rule, this is a law that that's just like AIMD principle, there is a square root principle. It's not mine, somebody else's, I don't know whose it is. But the square root principle simply says that if you have n people sharing, then each one can use 1 upon a square root of n of it, not 1 upon n, 1 upon a square root of n. So if 16 people are sharing, each person can use up to 1/4. Yeah.
I have a question around the first one.
Yeah.
Why is it RTT transmission rate and not like just one-way transmission rate?
Yeah. So basically, that's a very valid question, because what you want to do is you want to keep the source busy for the whole round trip. And so the source has to send so many messages so that it doesn't have to wait before the first acknowledgement comes, it is already ready to send the next message. So it is busy for the whole round trip. Right? Otherwise, if it is only halfway, then it will be just waiting here for nothing. Okay. So the buffering should be this much, and this is the full if there is only one user. But if there are any, so this is for one user, and this is for n users. All right. Now, how do we drop the packets? So the simplest thing would be that the latecomers are dropped out. That's what happens in the movie theaters. So drop tail. If you come, the house is full, you don't get the ticket, you go home. Right? That is drop tail. Well, it turns out that that may not be the right thing, because what is the fault of the packet? I mean, those who came early could have been, really overloading the network. So people said we will do random early drop. Random early drop means we start dropping even before the buffers are full. So even before the theater is full, when somebody comes in, we say, sorry, with 50% chance you can go home. All right, so we have a probability. With that probability, we say no, even if the seat is available. So that people who are coming late are not penalized for some reason. I don't know why. But anyway, so that is called RED, random early drop. Random early drop means even before the buffer is full, we depending upon the queue size, we find a probability, and with that probability we draw a random number and we say drop this packet. As the queue becomes bigger and bigger, the probability goes up, and after some time 100% probability, if you come, you are dropped. If the queue is full, there is no choice we have. See, we are not going to drop the packets which are already in the queue. That is possible too. I mean, we could start shooting the people inside the theater and say, sorry, we need some space. We need some space, but that's not a very nice thing to do. So generally we don't do that. If you are in, you are in. All right? But we can stop you at the door. So random early drop. So the routers measure the average queue and drop incoming packet with certain probability, and this is called active queue management. It is called active queue management because the previous thing, the drop tail, was passive queue management. You sleep and suddenly wake up and you find that the room is full and you stop dropping the packets. But active means you are awake all the time. Right? So there are two dropping policies, and there are advantages of REDs, and therefore RED is implemented everywhere. People have shown simulations and actual measurement and all that RED helps for fairness and so on and so forth. So RED is kind of preferred drop policy. Drop tail is not fair. Actually, drop tail, particularly if the traffic is bursty, then some sources which might send 100 packets right in the beginning, they might get in, and somebody who has sent only one packet will get dropped because they came late. And in the theater scenario, late and early makes difference, but in a routing scenario, there is no late thing. I mean, you just came at some time. There was no sort of started at a particular time, right? But you just came at a time when the buffers were full.
If you have a UDP stream,
Yeah. Yeah.
And like 3 TCP connections, and the UDP tries to send fast, and the TCP slows down.
Yeah.
And so the UDP can always utilize the entire.
Yeah. UDP wins all the time.
All the time. So if you want a fast application, always UDP.
Yes, you can play that game. So actually, then they are trying to design congestion control schemes for UDP. So that I don't think we will discuss those in this course because they are already done with TCP and UDP. But if you wanted to find out, then you go to IETF and they're talking about controlling UDP traffic. Because on one side TCP is nice and UDP is not nice, so you can't do that. Okay. All right. So summary of this slide. Everybody understands drop tail, red, and active queue management, right? All right. Then head of line blocking. Head of line blocking. So basically, first let's talk about what kind of switches there are. So in every router there is a switch. Inside the router there is a switch, hardware switch. It's a very fast switch. The switch, what it does is, the packets as they come in, they stand in the queue, and the switch looks at the destination address and looks up at this table and whatnot, and then somebody looks up at the table and then says, okay, it has to go to that port, and that has to go to that port. So then the switch does it in hardware very fast. Now, in some switches, you have packets queued at the input, so it means they wait until their turn to go. And in that case, what will happen is, suppose somebody wants to go to this position, right? And so the red packet wants to go there. However, this port is busy because somebody else is going there. Then what happens to the green packet? So the green packet has to wait, even though that port is available, but it has to wait because the red is ahead of you. I mean, you have gone to the grocery store queue where somebody has the problem with their credit card, and you are stuck behind them, right? Or somebody has a problem with the product that they just bought, and you are stuck behind them. So that is called head of line blocking. People who are at the head of the line, they are blocking the whole queue, right? Because the queue is first in, first out, and the person who is at the head is having some trouble. So why do you get there stuck there? Because the packets cannot be sent out of order. So every packet has to wait until its turn comes.
No, I mean the first packet that is blocked.
Or the red packet is blocked because somebody else is going to that port.
Oh,
So that line is busy. It's like only one person can talk to the port at a time, or one packet come to the port at a time. Yeah. Yeah.
On machines with like multiple virtual machines, do they like emulate this with software, or how does
Yeah. Okay. So if you have virtual machines on your computer, then you have all of this emulated, like virtual machine. Each virtual machine is a full machine by itself, and then there is some kind of router emulated, which will make one output interface. So yes. All right. So the key thing to figure out that really head of line blocking is not good, and you should avoid it in your designs. But first thing is to understand what is head of line blocking. Everybody knows what is head of line blocking now, right? When the person at the head of the queue is blocked for some reason. All right. So that brings to the end of this part. And the 6 key messages for this part, not the whole chapter, for this part of the chapter is that the forwarding is using the routing table to find the output port using the longest prefix match. So you know all of these words. And the routing protocols make those tables. ATM. I should delete that line, but I think I deleted the ATM slides. IP provides only best effort service. So, basically, let me just say what we missed. So there was a technology called ATM, which was developed by the phone company, so that it would provide quality of service, so that you could say, I want so much delay, I want so much throughput. And I spent quite a bit of time on that. Actually, I spent about 5-6 years on ATM research. However, it doesn't exist anymore. The technology didn't succeed, was not implemented, and is not there. So I skipped that whole part. There's a little bit in the book, but I felt that what is in the book is not sufficient to really explain everything. So I had a lot more stuff on my slides, but then I deleted that. So IP doesn't provide any of that. It provides no quality of service. You cannot say to IP, well, this packet is faster, that packet is first, or this packet is second. You cannot say anything to IP. So IP follows a principle called KISS. Everybody knows what is the KISS principle? Keep it stupid, simple, stupid. Sorry, keep it simple, stupid. Right? So basically, and that works. Because if you make it complex, it doesn't work. So ATM didn't work. Okay? And both Ethernet and IP follow the KISS principle. So that is what it is. So it follows. Routers consist of input ports, output ports, switching fabric, and the processors. We just went through the switching fabric. We showed you the three parts of the routers: the input port, output port, the switching fabric. The book has a little bit more detail. I expect that you can read all that. It's not critical. I want to spend time on the critical part of the chapter, so that's why we are moving on. And then we learned that the data grams can be dropped even if the queue is not full, and that is called random early drop. Random early drop. And then we learned that the head of line blocking. If you queue at the input, then that can result in head of line blocking. And therefore, when you design a router, you don't do input queuing, you do the output queuing. Means as soon as the packet comes in, it goes to the output queue and then waits there for as long as it's required. So there is no queue at the input. Okay? All right, so that's this part.